In this video, we review Fischer esterification reaction mechanism. The Fischer esterification reaction involves reaction of carboxylic acid plus alcohol under acidic conditions to give esters plus water. So a quick note before we start the mechanism: the Fischer esterification is an equilibrium process. Energetically, the products have nearly identical stability to the starting materials, and thus there is no driving force for the reaction. Remember that esters can get hydrolyzed in presence of water and acid, so this reaction can go backward to give us alcohol and carboxylic acid again. So how do we force the reaction to go forward? Well, we can use Le Chatelier's principles to drive the reaction forward. There are a few ways to do this. One method is to remove one of the products. So remove one of the product as it's being formed. Because one of our product is water, it's pretty straightforward to remove water in the reaction mixture as it is being formed. Or we can also distill the ester as long as the ester has a lower boiling point than the reactant. Another way to force the reaction to go forward is to use an excess of one of the reactants. So excess of one of reactants. Okay, so now let's dive into the reaction mechanism. First, let's establish the nucleophiles and the electrophiles. Well, the nucleophile is going to be the alcohol oxygen because it has lone pairs of electrons, and the electrophile is going to be the carbon of the carbonyl group. So remember, oxygen is electron withdrawing, so it's going to pull electrons towards itself, leaving a partial positive charge on this carbon. So this is going to be our electrophile. One quick note again, so remember that alcohols are not really strong nucleophiles, so for this reaction to go forward, we need to either make the nucleophile more reactive or make the electrophile more reactive, and we're going to do the second one. So we're going to make the electrophile more reactive, and that's the purpose of using acid catalysts. So in the first step, the oxygen is going to get protonated by the acid catalyst, and the oxygen is now positively charged, so it's going to pull electrons even more towards itself, and that leaves even more partial positive charge on this carbon, making this a stronger or more reactive electrophile. Next, the electrons on the oxygen are going to attack our electrophile, and because the carbon cannot have 5 bonds, the pi bond is going to break like this, and we're going to get our tetrahedral intermediate shown here. Now in the next step, all we're doing is proton transfer. So this oxygen is positively charged, and so it's not really happy because oxygens do not really like to be positively charged, so it wants to get rid of that proton, and one of these OHs will grab another hydrogen, because by doing that they become OH2 plus, which means that this is now a very good leaving group because it's just water. So this step, all we're doing is just proton transfer. So now that we have a very good leaving group, the electrons on this oxygen are going to push out this water, and this is the intermediate that we're going to get. So this is our ester plus water, which was our leaving group. So this is a very good leaving group. So in the last step, again, we have this oxygen that's positively charged. It's not happy. All we're going to do is just the deprotonation, where that oxygen is going to lose that hydrogen, and this gives us the ester plus water, and this is the hydrogen that the oxygen lost. So this is how we regenerate the acid catalyst. So let's just do a quick review. We started off with carboxylic acid under acidic conditions using alcohol. It gives us ester plus water as one of the byproducts, and because esters can get hydrolyzed under water and acidic conditions, we need to drive the reaction forward by either removing one of the products or using an excess of one of the reactants.